Good morning. I'm from Penn State University, where we have been working very closely, both across the university with faculty members in the Department of Material Science and Engineering, electrical engineering, as well as astrophysics, and along with a group at the Smithsonian Astrophysical Observatory to try and develop optics for next-generation X-ray telescopes. Overall, if you look at the current status of what we're working on being able to replace the relatively thick optics that have been historically used by telescopes such as the Chandra for producing high-resolution images. The optics in the Chandra, the glass is really very thick, and the net result is that it's quite heavy and it's literally difficult to launch a large number of reflecting surfaces. And so we're very interested in being able to replace those very heavy optics with optics that will provide the same angular resolution, but will be substantially thinner, so that we can simply fly more reflecting surfaces and increase the collection area. Current lightweight optics cannot achieve the required angular resolution. And so they also tend to, because they're thin and relatively large, they distort quite easily. And so it's necessary to be able to replace those thin optics with something that allows you to provide an adjustment for the deformations. And so the approach that we have been taking is to utilize the lightweight glass optics, but to marry to that a piezoelectric correction that allows us to be able to correct for deformations of those optics. Among the missions that would be influenced by this would be telescopes such as the potential SMART-X or X-ray surveyor. The approach that would be taken here would be to try and develop a set of nested curved glass optical surfaces, which are the reflecting surfaces for the X-rays, and to be able to have a very dense array of those surfaces which we can adjust real time to improve figure errors. The overall instrument would have microcalorimeters as well as high-resolution spectroscopy, and would allow a number of science goals to be achieved, as shown here. So this shows an example of some spectroscopy data from the Chandra telescope, where you have excellent angular resolution, but at present, because the collection area is really quite modest, there are many, many objects that one simply cannot image. And so the goal of this new technology is to basically be able to replace a Chandra-like telescope with something that has a signal-to-noise ratio roughly 30 times better. And there's a number of scientific goals here that this would allow us to begin to investigate. And so in order for this technology to be feasible, we need some way of preparing on these thin, slumped glass optics a corrector element. And the approach that we've taken to do this is to utilize lead zirconate titanate thin films. We deposit these by a sputtering process, as shown here. We choose the composition of the piezoelectric to maximize the piezoelectric response and dope it to achieve high lifetimes under electric field. We had to work relatively hard to drop the crystallization temperatures for these piezoelectric layers so that we didn't deform the glass on which it was deposited. So we have probably a 30-year history of being able to put these films on silicon substrates where we're much less temperature constrained, and so we've adapted the technology in the last few years to allow deposition on thin shaped glass segments as well as metal foils. What's shown here is the optic itself in a schematic form, where you have the glass substrate. This will be about 400 microns in thickness, with the reflecting surface of a chrome iridium layer. And on the other side of the glass is a continuous bottom electrode a layer of lead zirconate titanate, where we're currently targeting thicknesses of around 1.5 microns, and then an array of top electrodes that are, in this case, somewhere between 5 millimeters and a centimeter on a side, which we then use to correct the optics. So if I could ask you to go ahead and play the movie here, please. What you can see here is one of the test optics that we sent from Penn State to Smithsonian Astrophysical Observatory. And you can see here, as we progressively increase the voltage, the deformations that are associated with actuating 3 of those piezoelectric cells. And we're able to achieve deflections of several microns at modest voltages. For the most part, we're targeting voltages under 10 volts to simplify not just the ability to put large numbers of correctors on, but also drop the required weight associated with the electronics to do this. And so the previous figure was an example of a flat glass segment where we had piezoelectric coated on the thin glass with an array of piezoelectric cells on it. One of our next jobs was to be able to do comparable depositions onto slumped glass optics. So you can see here a pre-slumped glass optic. It's about a 220 millimeter radius of curvature, so appropriate for one of the next generation space telescopes. We deposited on, so this is basically the backside. So this is where the actuators are. You see a bottom electrode, the sort of magenta color here is the lead zirconate titanate, and you see an array of centimeter square top electrodes on this part. And what is very difficult to see is that from each one of these electrodes, there are traces that come out to the side that allow us to electrically address each one of the elements. And you can see here influence function data, where we've deliberately actuated one of the cells to produce a local deformation in the mirror surface. And you can see excellent agreement between the measured and modeled data. What this suggests to us is that we have deterministic control over the surface. And we've been working very closely between Penn State and the Smithsonian Astrophysical Observatory to look not just at the component development, but to try and think through the logic of how this would actually be held. And so this shows a schematic of the fixturing that would be required to hold one of those mirrors. Each of these mirrors will have many, many piezoelectric cells on the surface, where we have control over the influence function associated with each one of those cells by applying voltage to that cell individually. We've tried to spend a fair amount of time thinking through many of the engineering details of this. How would you optimize the mirror optical performance? And this shows a finite element calculation of the error amplitude of an optic from a previous generation telescope, where you can see the color changes denote deformations of that thin optic. And this shows the surface figure that we predict that we can achieve using 5 millimeter on a side piezoelectric cells. So in principle, this technology shows that you should be able to make a next generation X-ray imager that has about a half arc second resolution. But there are some real challenges associated with this, and the first of which is that each of the piezoelectric cells needs to be electrically addressed. So if we were to imagine a 40 by 40 array of piezoelectric cells, that means we need 1,601 contacts, one for the top surface of each one, and a continuous bottom electrode. And that becomes onerous, having to do the wiring off the device. And so working very closely with a group of Tom Jackson, we are trying to utilize the same approach that's utilized to make displays, say for your cell phone or your laptop, where you basically do a row column addressing and have a thin film transistor on the back of each piezoelectric cell. If you do that, then you should be able to individually address the rows and the columns, and that will allow you to actuate individual cells. And this would drop the required number of contacts for that same 40 by 40 array down to 81, which substantially simplifies the overall system. And so via some NASA funding, we've been working to try and demonstrate this generic approach. The thin film transistor material that we have chosen to work with is a zinc oxide-based material. I point here to the fact that zinc oxide or indium gallium zinc oxide electronics are now commercially utilized in display applications. We were particularly interested in these because they provide substantially better electrical performance than alternative transistors based on amorphous silicon or organic electronics. And so they're fast, they're electrically stable, and they're mechanically quite flexible. And so we were interested in whether or not we could take these electronics and integrate them onto the piezoelectric array for the adjustable optic for the X-ray telescope. The key to the zinc oxide thin film transistors is that unlike silicon, where the conduction band is really associated with the sp3 hybrid orbitals of the silicon, these are very strongly directional orbitals, and as a net result, if you degrade the crystallinity, as would be typical for a silicon that was deposited at a low enough temperatures to be integratable onto the flexible glass, you end up substantially reducing the electrical performance from mobilities of several hundred centimeters squared per volt second to somewhere on the order of 1 centimeter square per volt second. In contrast, oxide-based semiconductors such as zinc oxide, the conduction band is associated with the s orbital of the zinc, which is a spherical orbital. It's much less susceptible to degradation associated with the exact atomic arrangement, and as a result, it's much easier at low temperatures to achieve mobilities of around 20 centimeters squared per volt second. And so we've looked at being able to prepare zinc oxide thin film transistors on the adjustable optics. The zinc oxide itself is deposited via a plasma-enhanced atomic layer deposition, where we would, for example, have a pulse of the zinc come in, we flow continuously a weak oxidant, and then we pulse a plasma periodically to drive the decomposition reaction for that material. And I show here, we also deposit the dielectric, which we're currently using aluminum oxide by the same generic approach. And you see here a fabricated zinc oxide thin film transistor. There we go. This shows the functional electrical performance of such a zinc oxide thin film transistor on a glass substrate. You can see here excellent on-off ratios, so we're able to modulate the current by many orders of magnitude. The differential mobilities are on the order of 20 centimeters squared per volt second, and crucially, all of the processing is done at less than 200 degrees C. So we have at least a 300 degrees C window between the processing temperature of the piezoelectric and the processing temperature of the electronics. So we would not, in principle, expect the deposition of the electronics to degrade the underlying adjusters. And to investigate whether or not this would in fact be a problem, we have worked to prepare zinc oxide thin film transistors immediately adjacent to or directly on top of piezoelectric cells. I show here the typical cross-section and the material stack that are used in these thin film transistors. We typically, following preparation of the entire device, coat the entire surface with an aluminum oxide passivation layer deposited at 200 degrees C. And so we were able to do the fabrication. There we go. And this shows the functional performance of the zinc oxide fabricated directly on the piezoelectric adjuster. And you can see that the two processes are essentially agnostic to each other. So the functional performance of the zinc oxide thin film transistor is completely identical to what we would have had preparing that on a standard glass substrate without the piezoelectric cell. And we've looked very hard for changes in the piezoelectric performance. We have been able to find absolutely no impact on the permittivity, the loss tangent, the remnant polarization, the aging rates, or the piezoelectric constants. So it is possible to marry these two technologies without degrading the constituents. The next set of experiments that we did was to try and demonstrate whether we could actually use these thin film transistors for a row column address. And so I show here data for a zinc oxide thin film transistor prepared on a PZT actuated glass optic. And what we've done is to basically modulate the voltage coming in to the thin film transistor. So at this point, we turn the transistor on, and we hold the voltage then for some time. The turn on time at which we were able to, so basically what you're measuring here is the voltage across the PZT capacitor. We were able to turn individual cells on in the order of 3 milliseconds. We then held the voltage for some time and then turned the voltage off, and this is basically the voltage decay across the thin film, across the lead zirconate titanate, and that's associated with self-discharge across the capacitor. You can see that the time constant associated with this self-discharge is somewhere on the order of 70 to 100 seconds, so that we are able to retain the voltage for relatively long times. And what this suggests is that we have a gracious amount of time where we can hold the voltage with less than a 1% voltage ripple so that we can be able to control the figure where we go through and set by our row column addressing each of the rows in sequence. There we go. Goodness, this is a fussy one. There we go. So we have been working over the last year or so to try and be able to demonstrate on a test flat the integration of the zinc oxide thin film transistors for a row column address scheme on a 5x5 array of the piezoelectric cells. You see the mask layout here. Where the green cells are the piezoelectric elements, and the red shows the electrical contacts to the zinc oxide thin film transistors. The approach that we've taken to do this is to start with a 4-inch Corning Eagle glass. This is basically a display glass. The reality is those are available in up to 10 meter square segments, so gracious area if we ever scale to that size. We deposit on that the bottom electrode for the piezoelectric array, and then the piezoelectric with its electrode stack. And so we basically sputter deposit the lead zirconate titanate, crystallize it, then sputter deposit the top contacts using a liftoff approach to do the patterning of the platinum. On the entire stack, we spin coat a layer of benzocyclobutene, which is a photopatternable polymer. I apologize, but I cannot make this advance. Could you hit one, please? There we go. So there is the benzocyclobutene, which has been photopatterned. On top of that, we deposited the titanium, and then using plasma-enhanced atomic layer deposition, deposit both the zinc oxide and the alumina dielectrics. Those are subsequently patterned by a conventional contact photolithography approach, and then we lift off the titanium sources and drains for those devices and ultimately passivate with the aluminum oxide. Can you advance, please? There we go. So here is a patterned zinc oxide thin film transistor on a PZT optic for an X-ray telescope. You can see here excellent transistor characteristics, as well as the PZT showed in that case 100% yield on the centimeter square electrodes, which is reasonably good for a university laboratory. This is a picture of that first generation device where you can see that we have the 5x5 array of piezoelectric cells. It's difficult to see at this resolution, but there are row column addressing for all of those cells, and we've used an anisotropic conductive film approach to being able to do the electrical connections to a flex connect, which can subsequently be controlled using a standard electronics. We have also spent the last couple months working on electrostatic discharge protection of those devices, and so we have integrated on the mask pattern a much higher turn-on voltage thin film transistor, which is normally transparent to the system, so it's normally on, and so the voltage passes to the row column addressing. But if at any point there is a voltage spike that runs through the system, that zinc oxide thin film transistor and the protection circuitry shunts that voltage away from the higher sensitivity zinc oxide TFTs on the mirror element itself, and we believe this will significantly improve the final reliability of the device. So if we look at our current development status, we have demonstrated the ability to put functional piezoelectric thin films, which can be integrated with the control electronics to enable adjustable optics for the next generation space telescope. Continuing to advance the technology would probably require on the order of several millions dollars to get to a fieldable system. The overall approach of integrating low-level control electronics with the adjustable surfaces is enabling for a fairly wide variety of applications. So we've tried to illustrate for you here that this could be a game changer for the case of X-ray optics. It could enable future generation devices with the same angular resolution as the Chandra telescope, but with vastly higher collection areas. But in general, the approach is equally appropriate to look at visible or infrared adjustable optics as well. This does significantly simplify wiring schemes for other actuator arrays, including, for example, the arrays for biomedical ultrasound or for pressure arrays, the ability to measure pressure spatially. We've also demonstrated that you can utilize the zinc oxide thin film transistors for active rectifiers. And this is perhaps germane for self-powered sensors where we actually utilize vibrations to power the piezoelectric, dump that energy into the battery. Because the piezoelectric, when it vibrates, will have both, will output an AC voltage that needs to be rectified, and you can do all the low-level rectification relatively straightforward fashion with the integrated electronics. And I think there's a variety of other possibilities that may potentially be of interest to NASA as well. So to summarize, we have successfully demonstrated that you can grow piezoelectric thin films with large piezoelectric responses on thin glass optics. We've demonstrated high yields on both flats and slumped optics. And we've demonstrated the ability to pattern those electrodes at the spatial scales that are required. And we're very thankful for the funding for this work that's come from NASA and the Moore Foundation, as well as Smithsonian Astrophysical Observatory. The piezoelectric thin films allow you to correct optical distortions in thin, lightweight glass mirrors. And we predict that we should be able to achieve about a half arc second resolution. The approach is deterministic so that you can actually control using the known piezoelectric responses starting from a deformed surface. And we currently believe we are at a TRL3 level. We have a plan in place so that we hope to get to TRL4 by the end of fiscal year 16 and TRL6 by 2018 in preparation for the 2020 decadal survey. So there's my contact information, and I will take any questions that you have.
Hello. Just a couple quick questions. One is, what's the stress in the piezo layer, and how do you intend to compensate for that stress? Is this based on the chromium layer that you deposit prior to the iridium layer? And have you demonstrated the functionality of the piezo with the iridium X-ray reflective layer on?
So the piezoelectric stack goes down with a tensile stress on the order between 100 and 150 MPa tensile, and we do compensate that with a chrome iridium layer on the backside, and yes, we have demonstrated that.
I may have missed this, but you mentioned the thin glass mirrors. How thin are the mirrors getting to?
400 microns. So that's what we're currently targeting. The glass is available at substantially thinner thicknesses. And so if there was any need to go to a more deformable substrate, that absolutely could be done. The thinnest substrates on which we've deposited high-strain piezoelectrics are around 25 microns in thickness. So we can handle quite thin.
And I was also curious about whether there was a material choice of white glass, or can these, active optics be put on a different type of substrate?
That's an excellent question. So we have demonstrated that we can do these adaptive optics, or we can do the deposition of the piezoelectric and make functional devices on silicon, glass, and nickel foils. We're relatively flexible in terms of what our deposition, on what we deposit on. When we do deposition on a material like nickel, we end up needing to put down a few intermediate passivation layers that prevent subsequent oxidation of the foil. But that's quite generic, so that we could do this on essentially any metal surface that will tolerate temperatures of at least 550 degrees C. So aluminum is hard, but stainless steel, any other surface, we're relatively capable of handling those as well. Thank you.